Hello everyone, I'm Mehrdad Khani and today I'm going to talk about real-time video inference on edge devices via adaptive model streaming. This is joint work with my advisor Mohammad Alizadeh and my colleagues Pouya and Arash at MIT CSAIL. A copy of our paper is also available online on arXiv. Performing real-time inference on video frames has a wide range of applications, especially when it comes to edge devices like smartphones. Many AI-based applications expect to run basic computer vision models such as object detection or semantic segmentation in real time. And by real time, here we mean being able to process at least 30 frames per second with less than 100 millisecond latency. Such stringent processing speed requirements create significant challenges on edge devices, as they have much lower computation power compared to the state-of-the-art accelerators that run in the cloud servers. To get a sense of how the gap between the edge and cloud server compute power impacts the inference at the edge, let us have a closer look at an object detection task as an example. Here we refer to a figure from Jianji et al.'s CVPR 2020 paper, which shows the average precision score on the y-axis and the total number of floating point operations or flops on the x-axis. Each point in this figure corresponds to an object detection DNN model. We see that a higher number of flops is generally resulting in higher APS scores for state-of-the-art models. These models cover a wide range of computation resource requirements from 33 billion to 1200 billion flops. Yet, the question is, which of these models can be run in real time on edge devices? Unfortunately, the answer is none of them. Almost any model with more than 1 billion flops cannot run in real time on any of today's edge devices. Hence, existing solutions either use smaller models like MobileNet, for example, on the edge device, or offload the inference to a remote powerful machine, which is, in this approach, the edge device sends the video frames to the remote server and receives back the inference results. However, using lightweight models is usually accompanied by a notable loss in the accuracy metric. For example, in the same object detection task on the same dataset, we observe here that mobile-friendly lightweight models can only achieve an APS score of up to 29%, while the state-of-the-art models could achieve a 2x better score. This significant performance loss for lightweight models is not unique to object detection only, and it generalizes as well across a wide range of machine learning tasks. As mentioned earlier, another approach to video inference on edge devices is remote inference. However, it is very brutal to have real-time inference in remote schemes. And this is mainly because of three principal obstacles in this approach. First, video codec latency, network delay, and server computation congestion in total can easily exceed 250 milliseconds in latency. Second, the real-time latency requirements do not allow for most effective video compression techniques, and hence we usually end up in high bandwidth requirement. Third, network outage is a typical characteristic of wireless communication systems, that leads to poor robustness of remote inference. In summary, there have been two general approaches to the inference at the edge in the past. However, they either lack accuracy or they cannot run in real time. We propose the adaptive model streaming, a framework that enjoys both large models' accuracy and lightweight models' real-time on-device inference property. In AMS, we use a lightweight model to perform real-time on-device inference at the edge. Meanwhile, client continually sends sampled training frames to a server machine in the cloud to adapt a copy of the lightweight model for the client's context at each particular point in time. We use supervised knowledge distillation for the purpose of model adaptation here, where our lightweight model tries to mimic the behavior of the state-of-the-art teacher model on the sample frames from the client. We then periodically stream the lightweight model updates from the server to the client once every 10 to 100 seconds. AMS effectively reduces the discrepancy between the lightweight and the state-of-the-art model's output for each scene. For example, for the task of semantic segmentation, where we need to classify every pixel in each frame, we have shown here some sample results of AMS performance on real-world videos. Columns from left to right represent no customization, one-time customization, and AMS. Also for reference, the results for large, expensive models are shown in the last column. As these results visually explain, AMS keeps tracking the state-of-the-art model performance. For example, please notice the sidewalks in the second row, which are highlighted in orange color. Our edge model, which is pre-trained on Cityscape's driving scenes dataset, tends to initially use simpler features for detecting sidewalks. However, the best model seems to use richer features for this purpose, and it can successfully transfer its knowledge to our lightweight model at this particular scene. As we see in the second column here, one-time customization in which we adopt the model only once on the data from the first minutes of the video is also not good enough. This suggests that a continual adaptation of our lightweight models is generally needed in practice. To get an intuition of how this continual adaptation helps, let us look at a toy example. As a simple example, consider a scalar regression task. Suppose we are given a simple time-varying triangular input sequence x of t, which periodically sweeps between -1 and 1. We are going to predict an output y of t, which is generated by a deterministic function of the input y of t equals f of x of t. Notice that the characteristics of function f changes significantly over its domain between -1 and 1. However, the regression task exhibits temporal locality, by which we mean x of t changes gradually over time, and the regression problem is similar in nearby time intervals hence. Video inference exhibits a similar temporal locality because the scenes in a video usually change gradually over time. Further, at each point in time, we are going to train a model over the data from the interval t minus tau prime to t, and use it to estimate f of x over the interval t till t plus tau. We refer to tau prime as training horizon. To see how the choice of a good training horizon relates to model complexity, we will use two models of the polynomial family to predict y given x at each time. We choose our small model to be linear with polynomial degree of 1, and the other one has a much larger degree. As we expect, the large model works better on a larger training horizon, which is shown by tau prime here, and it overfits on smaller horizons. On the other hand, the linear model does not have the capacity to fit the data over a long time horizon. However, by continually adapting the model based on a small training horizon, it is able to make much better predictions. This example illustrates the importance of picking a training horizon that is well matched to the model capacity. Smaller models benefit from a shorter training horizon, or in other words, they benefit from more localized customization over time. Before moving into the details of AMS design, let us a little bit discuss how AMS connects to online learning theory. As you may have already noticed, our work is closely related to online learning algorithms for minimizing dynamic or tracking regret. Dynamic regret compares the performance of an online learner to a sequence of optimal solutions. Adequately close, our goal is to track the performance of the best lightweight model at each point in time. Dynamic regret problems in general have lower bounds that relate regret to a measure of the complexity of the optimal sequence of decisions, such as how quickly the best model parameters change with time. As video scenes change slowly, the best model parameters may change also gradually in time, which promises online learning to be effective in practice. Several theoretical works have studied online gradient descent algorithms in this setting, with different assumptions about the loss functions. Other works have focused on the expert setting, in which the learner maintains multiple models and uses the best of them at each time. Our approach is based on an online gradient descent because tracking multiple models per video at a server is expensive. Model streaming framework faces three unique challenges of its own. These challenges are generally related to the real-world computation and network resource limitations. AMS design fully identifies and addresses these key challenges as follows. First, naively sending a simple lightweight model with 2 million parameters every 10 seconds would require 3.2 megabits per second of bandwidth in the downlink from the server to the client. AMS effectively reduces this bandwidth by actively choosing the best subset of parameters to train at each update. Second, AMS requires the sample training frames to be uploaded to the server. Sending these frames to the server in real time would require order of megabits per second of uplink bandwidth. However, AMS exploits the temporal locality of video frames by smart buffering of the sampled frames and applies efficient video compression algorithms without having any impact on the inference path. This results from the fact that the server is not involved in any latency supersensitive processes in AMS compared to other remote inference-based schemes. And we should also be aware of our GPU utilization at the server. Running a GPU in the cloud, like something like NVIDIA Tesla V100, currently costs at least $1 per hour. Hence, it is important to serve multiple edge devices per each GPU and keep up a high GPU utilization to bring down the overall per client costs. We will next discuss the AMS algorithm for the downlink bandwidth. For a detailed discussion of AMS uplink and server utilization solutions, please refer to our archive paper. AMS uses a coordinate descent algorithm in which it selects a fraction of model parameters to update at each training phase based on a parameter selection strategy. It then only sends those updated fraction of parameters to the client side. For the parameter selection strategy, AMS uses the gradient signals, which we call gradient guided strategy here. Gradient guided strategy builds upon the ADAM optimizer update estimates. The key insight here is to only allow update for the parameters which are going to experience largest changes. However, we don't know those parameters prior in time at each training phase. Hence, each training phase of AMS consists of k training iteration, which is typically where k is typically between 10 to 20 iterations. At each iteration, we compute the gradients on our mini batch of samples from the training horizon. This horizon's length generally depends on the lightweight model capacity and the inference task at hand. We then update the ADAM optimizer momentums and calculate the optimizer updates for all parameters. Finally, we apply those updates which are allowed by our parameter selection strategy at this training phase. At the end of each training phase, we pick a fraction of model parameters with the largest update magnitudes in the step 1b above. These coordinates will be trainable, and these coordinates and only these coordinates will be trainable for the next training phase. Keeping track of potential ADAM updates for the entire model parameters at step 1b helps us maintain a stronger signal of which parameters will have a higher impact on the loss function in each training phase. For the rest of this talk, we are going to see AMS results on the task of semantic segmentation as an example of a complex task in computer vision. For this purpose, we use DeepLab V3 with Exception 65 backbone as our teacher model and a DeepLab V3 with MobileNet V2 backbone at an input image resolution of 512 by 256 as our lightweight model. Both of our teacher and lightweight models are pre-trained on Cityscape's dataset. Our lightweight model runs at real time at 30 frames per second on Samsung Galaxy S10 Plus mobile phone's GPU with less than 40 millisecond latency. We evaluate our approach using 7 real-world videos from YouTube that span a variety of outdoor scenarios, including fixed cameras and moving cameras at walking, running, and driving speeds. For each video, we manually select 5 to 7 classes that are detected frequently by our best semantic segmentation model. For more information about the video classes, please refer to our paper. AMS achieves 5 to 17% mean intersection over union or MIOU scores improvement than compared to pre-trained lightweight models with no customization. In order to evaluate the impact of continuous adaptation of models, we also compare AMS with a one-time customized model over the first 60 seconds of each video. We observe that compared to one-time customization method, AMS still achieves 0.1 to 15.5% MIOU improvement. As expected, AMS continuous adaptation have more significant gains compared to one-time customization in cases which the video scenes experience higher dynamics. For example, the 0.1% MIOU difference between the AMS and one-time customization, which is our smallest gain for AMS, corresponds to this interview video, which has a relatively static scene compared to other videos in our dataset. As you can see, the scene does not change very much for this video. To evaluate the effectiveness of gradient-guided strategy, we compare it with the following baselines. Our simplest baseline is to select the target fraction of model parameters either from the first or the last layers of our model. We also consider the hybrid case where we select the parameters equally from both first and last layers. And finally, we also compare the gradient-guided strategy with a random strategy where we uniformly select the coordinates from all over the model. As we see, the gradient-guided strategy outperforms all other strategies in all settings. Random strategy, as the second best, tells us what we need for our model adaptation is perhaps more than fine-tuning the final or the last layers. Also, we observe that the gap between the gradient-guided strategy and the random strategy increases as we decrease the fraction of the model parameters we are allowed to change at each phase, which in fact shows the significance of our gradient-based signals. In total, using the gradient-guided strategy, we require only about 200 kilobits per second of bandwidth for streaming the model updates from the server to the client. To put this bandwidth requirement in perspective, please be aware that YouTube recommends bitrate range of 300 to 700 kilobits per second to live stream videos at the lowest resolution, which is 240p. AMS also scales to support 7 simultaneous clients with a single NVIDIA V100 GPU at the server with less than 1% loss in MIOU, making its server cost feasible to be deployed at the scale. In conclusion, adaptive model streaming improves the performance of real-time video inference on low-powered edge devices. By handling bandwidth issues and making smart decisions about training, AMS opens up the road for numerous real-time applications at the edge that used to be almost impossible in the past. On the task of real-time semantic segmentation as an example, AMS shows a rise of up to 17% in MIOU score using a mobile GPU, which can be a significant improvement for the quality of real-time inference on edge devices. Thank you for listening to this talk. Please feel free to reach out if you have any questions via email or either Twitter account. Thank you.